So welcome to this lecture in the course Digital System Design with PLDs and FPGAs. In the last lecture we have completed the examples on VHDL. Then we started with some issues in the finite state machine or the controller. We have looked at how to bring the state machine to a starting state using a reset, very simple thing. But if you forget, then it can be problematic. Okay, this is like you make a cable and you want to crimp a connector, and normally there is an outer ring, and if you have not put and you have gone ahead and crimped, then you realize that you have not put the outer connector, outer turn or something like that, then it is tough. So something like that. So you should not forget to bring the state machine to a starting state by putting the reset. Second thing we have looked at is what is the kind of most appropriate clock frequency for a controller, for a state machine. We have looked at the maximum frequency, but then that's not a good idea to run the state machine at the maximum frequency. It will dissipate a lot of power. Suppose the data path is running at a much lower frequency. So what should be the criteria, how much you can bring down the clock frequency of the state machine, and what are the issues associated with it, and that is what we have seen. I mean, we haven't completed, but then we kind of set the case for minimum clock frequency and we have seen some effect. So I will just have a quick glance at this last lecture slide. I will not go back to VHDL because we have done quite a few lectures on that. You must be thorough with it. So let us move to the slide. We will see the state machine part as a revision, then we will continue. So let us look at the slide. So this is the slide on power on reset. So this is the state machine kind of structure. You have the flip flops which gives the present state, and that combined with the input will give the next state using next state logic. The present state is decoded to produce the outputs. Sometime some output may be just a function of present state, and some output could be a function of the present state and input. And as we continue this lecture, we will have a look at what is the difference, or what are the features of this Moore kind of output and Millet kind of output. We will see that. So I said that suppose the flip flop you are using in the technology, suppose you are implementing the state machine in FPGA and the FPGA flip flop as an asynchronous reset, or you are making it in VLSI chip and the technology flip flop has asynchronous reset, then it is easy to use that asynchronous reset. It is very quick. As soon as you assert the reset pulse with a minimum delay, the present state become the 0. So naturally the starting state can be all zeros. That is the most easiest thing to do. Suppose you start with the state 001, then you may have to reset some flip flops, set some flip flops. So when it comes to the state assignment, it is always easy if you can assign the starting state as all zeros, okay, depending on the number of flip flops. So asynchronous reset can be used, and suppose we do not have that asynchronous reset in the flip flop, then we have to look for synchronous reset. The advantage is that the synchronous reset can be an input to the next state logic, and the game is that if it is asserted, then we say that the next state is 00 or the starting state. Okay. In this case you have an advantage that you need not reset to 0 when you have a sync reset, since it is part of the next state logic. You could make it easily to any state, okay. But if it is 0, it is all the more convenient, and we have also said in tune with the kind of synthesis we are doing at the RTL level, it essentially means like given to a synthesis tool, and you know that the reset has priority over all other inputs, then it means that ultimately the circuit is nothing but you have a 2-to-1 multiplexer at this stage with the reset as the select line. When it is 1 the 0 goes, when it is 0 the normal thing happens. Okay, that is, I mean, we have seen that kind of synthesis. I mean, that is what, even if you write equation, an equivalent circuit is going to come at the output. Instead of a 2-to-1 mux, maybe a simple AND gate comes, and the sync reset can be, if it is active high then it can be inverted and can be given to the input of the AND gate. Suppose if the number of flip flops are 2, then there will be 2 AND gates, and the next state inputs are going to the D1 and D0 will go to one of the inputs of each AND gate, the other input goes to the inverted sync reset for active high and so on. Okay, I suppose that is simple enough for you to work out. I just gave some detail about how it is going to be implemented when it is really worked out, the equations are worked out. So that is about the power on reset, and we have looked at the clock frequency, and the question was that what is the ideal clock frequency for the state machine. Okay, now we know that what is the maximum. Okay, it depends on this path and this path. Okay, so this path going all the way up to some register or up to here, since we don't know where it is going, we will consider up to here. Okay, so it means that the clock period should be greater than the TCQ, because a clock comes, it takes TCQ delay, then the next state logic delay, and that has to come here setup time before the next clock edge. So the T clock min should be greater than TCQ plus T next state logic plus T setup, or it could be TCQ plus T output logic, because even if it is something directly used here, say like it's crazy if this path works properly but the output does not get a chance to become active, before that it goes to the next state. I mean, everything works internally fine but the output kind of does not have time to get decoded, then it is a bad thing. So that is a maximum frequency, that is what is we are putting it here. So we choose max of 2 paths, TCQ plus TNSL plus TS, everything max. Okay, and this is the TCQ plus TOL max, and you should know that even when we use the tool, there are the clock period we use a maximum time delay, and for the whole time violation we use the minimum delays. Okay, because it is the whole time violation happens with the same edge. So in the tool when you simulate you have the opportunity to choose the fastest delay or the slowest delay and all that. Corner cases can be chosen when you do timing simulation. Maybe when we work with the tool I will show you how to do that. So that is the maximum clock frequency, but then we said there is no kind of point in clocking at the maximum clock frequency because it dissipates a lot of power, and moreover we have some data path which is being controlled by this controller. All these inputs are coming from somewhere in the data path, and these outputs are going to the data path. So naturally, and that data path is working at some frequency, we optimize or we maximize the clock frequency in the data path to get maybe the highest throughput in some application. Okay, so there is no point to kind of like suppose that is working at 100 megahertz, maybe it is futile and a lot of power wastage if we work at 1 gigahertz clock frequency. Okay, so the question is that what is the minimum we can do. Okay, like given known, like if the data path is given, then what is the minimum clock frequency we can choose, and that was the question. And to illustrate I have put some kind of simple picture there. Assume the data path, the data path outputs which is going to the input of the state machine. That means again in this picture we have suppose 3 inputs in1, in2, in3 coming from some part of the data path, okay. So I have put that, okay. So and to understand the problem we have made it very kind of simple and very symmetric, okay. We have put square waves like clock which is not the real life at all, that but we can, as I said, when you analyze always go for the simple case, always go for the symmetric case, regular case, so that once you grasp the underlying issue, the basic how to solve it, we can extend it, extrapolate it to the real life, okay. I have cited an example. Suppose you have working with the linear algebra with matrices and you are probably working with eigenvalues or linear transformation or rank of a matrix, and if you work with a 5 by 5 matrix and try to get some intuitive feeling about it, it may not be possible. But then if you say work with a 2 by 2 matrix or a 3 by 3 matrix, it is possible that you can come to a 2 dimensional or a 3 dimensional graph you can draw with the vectors, and you can make out, suppose you are applying some linear transformation, what is happening to the vector can be easily understood. Then if you have grasped that basic, then you go to 10 by 10 matrix, that at least that clarity will come into the picture. You can't draw a kind of a graphical picture of the 10 dimension, but if the matter is clear in 3 dimension, okay. I am talking about the geometry to make the life easy, but need not be, okay. Not our subject, directly not related, but then you know some people are comfortable to work with the algebra alone, that you don't use such kind of isomorphism of going from algebra to geometry and back, but anyway in geometry probably you are limited with the 3 dimension and so on. But anyway, coming back to our problem, we put very simple symmetric case. Let us assume, yeah, I have chosen very cleverly kind of manipulated case. In 1 is a some kind of clock kind of waveform, in 2 is half of that, in 3 is half of that, the clock period. So the frequency is twice and this frequency is twice of that. So this is the scenario, this is going to the state machine and we have put something like this, okay. Let us assume the state machine clock is this, and we have found absolutely no problem, like at this positive edge the state machine is in some state, it detected that in1 is 0, then in1 has changed, in the next clock edge yes it has transited, maybe we are in a state looking for this input to go from low to high, absolutely no problem, because if we say in a state in 1 bar you remain there, in 1 you go to the next state, and that will happen perfectly because at this stage it will be in that particular state, but when the next clock edge comes it finds that the in 1 is 1 and it will transit to the next state. Maybe we will make some output to respond to this event, and that is how we control, and here again it is 1, then it is 0. So it is able to track all the changes in 1, and look at in 2, absolutely no issue. When this clock edge comes, in 2 is 1, then this comes, in 2 is 0, then in 2 is 1, no problem. But look at in 3 and what happens, you know, the clock edge comes to the state machine, it detects a 1. Suppose there was a you know condition that as long as in 3 is 1 remain in this state, and if in 3 is 0 go to the next state, and you see that it has gone to 0, then it has gone to 1, but at the next edge it is still 1, in between it has gone to 0, it has come to 1, next clock edge our state machine still is detecting that in 3 is 1 and it will get stuck at that state, it will not even proceed to the next state, and it is stuck there and waiting forever for this particular input to go low. So you get the problem now. So this clock is not able to detect the change in this particular input. So for it to be detected, we know that at least one active clock edge should come in this period. Okay. Suppose an active clock edge just come here, we should have an active clock edge somewhere here. So like you should have an active clock edge in this period and another in this period. So naturally one clock period, suppose it is good if we can have one edge here and one edge here and so on. So we should have at least one edge in this period. That can happen only if the clock period of the state machine is at least less than this particular width. So you see this is the maximum frequency input to the state machine. The clock period is from here to here. Okay. So you take the half the clock period. So the period of the real FSM clock should be less than half the period. That means the frequency of the state machine should be twice that of maximum frequency input. Okay, that's a game. Okay. So so that is it. Okay. Now maximum clock frequency should be greater than the twice the maximum input clock frequency. Okay. It sounds like in a kind of Nyquist criteria, because in Nyquist criteria you say which definitely we are talking about the transform, the frequency domain. You have a signal and you want to sample it, and you know the highest the clock frequency or highest frequency contain the sine wave, then you should sample at twice that so that you can recover it. Something similar to that happens. It should not be surprising because we are sampling the input, though we are talking about the digital domain where we are talking about binary signals, not the analog signals and so on. Yeah, this happens because we are sampling the inputs, and first thing is that now let us relax our criteria. Earlier we said okay, we assume that yes, it is fine, it is like a regular square wave, but in real life nothing like that happens. So it is sampling the inputs. Input may not be very periodic waveform, but you have a pulse width, like you have a narrow pulse, that shouldn't be the criteria for choosing the clock frequency, because it can be stretched. And the game is that I will show a picture. Suppose this is the input, say the pulse width is 10 nanosecond. Okay, assume that it is 10 nanosecond. So you will have suppose this is the next pulse come with after 1 microsecond. Okay. So the clock frequency, the frequency of this signal, it may not be regular waveform, but assume the minimum time period between them is kind of 1 microsecond. Then we can say the clock frequency, the maximum clock frequency is kind of 1 megahertz, but this is 10 nanosecond. Okay. Now if we choose a clock period to kind of detect the change in this input, because this is coming to the state machine, we should detect that it has changed the state. Okay. Now to detect that we need a clock period which is only less than 10 nanosecond. That means this clock frequency will be 100 megahertz, but the input frequency itself is only 1 megahertz. Okay. So but the game is that we can kind of stretch this pulse, because the next pulse come only after 1 microsecond. Maybe it is even possible to stretch all the way to 500 kind of nanosecond or anywhere. Okay. And you can use a much lower clock frequency to detect this change at the state machine. So this is possible, but like it depends on the application. Suppose there is a requirement, some event has happened and this pulse has come, but say the controller should respond to that event within say 50 nanosecond, then you cannot arbitrarily stretch it. We have to use a clock frequency which is kind of the period should be less than 50 nanosecond, because like after the input changes within 50 nanosecond the state machine should respond to it, then the clock frequency should be chosen according to that requirement. So that is what is written here. The pulse width should not be the criteria, it can be stretched. How fast to respond to the event should be the criteria. Okay, so all these the problem is that many a times you read in the textbook, you get a very simplistic kind of solution disregarding all these issues. And even in real life, when you interact, when you work with a specification, many a times these kind of requirements are not clearly spelled even by your the customer or the user, or it may not be clear. You go ahead, implement something, then you deploy it, then you realize that. So it is very important to ask, to be aware of these issues, ask the right question when you kind of form the specification. And it is very important when you design some complex system to write these specifications, the requirements, in as much as details as possible. And there are standard format requirement specification, there could be standard formats, but I am not talking about the format. These formats, the standards and all helps, but even if it is not very organized, very systematic, writing it down, writing the requirements clearly, drawing some waveforms, writing some tables bring clarity to the scenario. Of course you can use some kind of documentation standard because it helps you to use standard tools to manipulate that. Like in a team nowadays it is all connected environment, so if you use a tool, everybody can look at the tool, multiple fellows can work on the same kind of file and so on. So that is helpful, but the primary thing is to be aware of these issues and bring clarity to the scenario. So let us look at this scenario, particular scenario where there is a pulse, and I will show you a kind of circuit how to do this stretching, okay, which is frankly not a very practical in the sense there are better ways to do it. So let us at the beginning just for the argument's sake see a simpler very simple circuit to stretch this pulse by whatever width you require as per your requirement. But I mean practically we don't use that. I will show you a better circuit after that, but this is to stress the point, okay. So one other thing is that here we talked about a pulse being detected, okay. Maybe there is no timing requirement, great timing requirement, it has to be detected before the next pulse, then you can stretch it to any limit and you detect it whenever you want before the next pulse, okay. But otherwise you say the pulse width is 10 nanosecond, but it has to be detected within 500 nanosecond, no issue, you stretch it halfway then you can detect it, okay. But it may happen that you may have to kind of you have a timing pulse, okay, and you have to detect it with certain accuracy. So if you remember in the case study we have discussed with respect to the ADC controller, we had just before this lecture we had a case study where we wanted to have a controller which controls an ADC to give the start of conversion to ADC and store the sample in a memory, okay. There we said that the write to the FIFO should be of certain width, and we have decided to put a counter outside, and the counter will give a count from 0 to some particular count, and we will decode that count and give back to the state machine, okay. And state machine will detect that change when it reaches that count and stop that write pulse, that was the idea. So we are in a similar situation, I am showing in the picture. Of course I am showing a kind of again an little ideal case. So let us assume this is a timing pulse we have started this pulse at this point and the state machine is looking for the end of the pulse, okay. But say this is some few say 500 nanosecond, but this being a timing pulse there has to be some accuracy on it. Suppose we are giving a delay like around 500 nanosecond, and suppose the state machine is sampling this pulse with a clock period, because this pulse is going high here, going low here. Suppose we use a clock like this, it looks perfectly fine, because this clock earlier would have detected that it is 0. Then this clock edge it is detecting that it is going to 1. Then at the next clock edge it is detecting that it has gone to 0. But our aim was to somehow capture this delay with certain accuracy. But what happens now, what we capture is that we will check at this active edge that it is 1, this active edge it is 0. So what time we detect, the state machine detect is this time period, not this time period, okay. So that is the issue. And suppose you use a higher clock frequency, little more higher clock frequency, there are positive edges here. So we are sampling at all edges. So here before it was detected it is 0, at this point it detects that it is going high, and you see here it is 1, here it is 0. So here if you see that the real timing pulse was this, and here the pulse width is this. So we are much closer here. Suppose the requirement is that, suppose this is kind of say assume that it is 100 nanoseconds, and this has to be detected with a kind of accuracy of say 90%, okay. So the error should be 10 nanosecond, okay. So assume that means this should be detected within 10 nanoseconds. So it tells that the clock period should be kind of in that order, the clock period, clock edges should come in kind of within 10 nanoseconds. So that is what is I have written, to detect a pulse with certain accuracy minimum clock period should be less than the error requirement, okay. This is quite intuitive, but when you do many complex things you forget, you can tend to forget this. It is very natural that if the counter is working with 100 megahertz and the state machine which is controlling that counter is working with a 1 megahertz, you know that there is something wrong. The counter is changing state at 10 nanosecond, and the state machine is looking at sampling at 1 microsecond is something not acceptable. So that is what is the game is. So this should be kept in mind as far as when you have a timing requirement. But in any case, but to make an assumption that everything should be greater than any frequency used in the data path will be a over simplification, and nowadays you have lot of constraints on power, the timing and all that. So it is better to choose the optimum clock frequency which minimizes the power dissipation and many other things like that. So that is about the accuracy of a timing pulse. So let us look at this scenario. We have a pulse, and which is actually the frequency is low but the pulse width is very narrow, and if you just consider the pulse width we will end up choosing a clock frequency for the state machine which is very high. But if you stretch it, because the frequency is very low, then you are able to use a higher clock frequency, lower clock frequency for the state machine. So to illustrate the principle I will show a pulse stretching circuit, then we will come to more practical circuit, okay. So let us keep look at this pulse stretching. So what we do is that this is a pulse catching flip flop. You see this flip flops, and this is a pulse, in this case a narrow pulse come, this is the input, and with a very low frequency the pulse come again, okay. And if you kind of concentrate on this pulse width, then you will choose a clock period which is less than this width, and that could be very high, okay. So assume that we want to stretch it to kind of somewhere here. So what we do is that we have a clock and reset, but the clock goes to this flip flops, but this catching flip flop has the clock as this, it takes this pulse as the clock and the D input is given to 1. Okay. So what happens is that when the pulse come, this S detect, so I am calling this DIT and this is synchronous detect. Synchronous detect, you see that it goes high. Okay. So the detect comes on the next clock edge. So here it goes high and the next clock edge that is shifted here, and in the next clock edge it is shifted here, that is what is shown here. It goes, output goes high, in the first clock edge it comes here, in the second clock edge it comes here. The moment it comes here it goes back and reset this game and this goes low. Okay. So this pulse is stretched by 1 clock period, because it looks as if it is 2 clock period, but it cannot be 2 clock period because we are not sure when the pulse is asynchronous to this clock. So it can come very close to this kind of this clock can come very close to it, and that is why I mentioned it is not a very practical circuit. I will show a practical circuit soon, but this is to kind of understand the principle. So we give 2 flip flops to get a 1 clock period stretch, so that is how it is stretched. So at the beginning it is reset, everything is reset, and then the pulse come, it is kind of stretched by at least by 1 clock period. You want to stretch it by 2 clock period, you put 1 more flip flop and so on. Okay. Not a very practical circuit because there could be timing issues at this point when the input comes here with this flip flop. Maybe if you put a chain of flip flops it gets resolved. We have not seen what is that timing issue, but so I am not able to kind of discuss that now, and it is problematic. It is not a very practical circuit. Suppose you want to stretch it to some kind of 10 times a clock period, then it is not a very kind of practical circuit. But then you might ask, I mean, why to stretch it, and you reduce the clock frequency and so on. So we will look at a more practical circuit. So that is using something called a pulse to level converter and a level to pulse converter. That means the basic idea is that when we have a pulse, instead of just stretching it, when the first pulse come we will make an output of this some circuit to go high like that, continuously high. The next pulse come, that high is made low. Okay. So there will be between the pulses you will get a kind of square wave, and what we do is that at the state machine, when it goes high we will convert it into a pulse in terms of the clock frequency of the state machine. Okay. Which could be decided by some other input. Okay. We are not sure, this input is very low frequency, maybe there are some other input which is higher frequency than this, that will decide the clock frequency of the state machine, and using that the pulse going high, that will be converted in the FSM to another pulse which is wide enough to be detected by the state machine. Okay. That is a game. So what we will see first, how to convert a pulse to a level. So that is what is very simple. So assume that this is a pulse. Okay, I have not shown a lot of kind of gap, but assume there is a gap, then the next pulse come, and this is a D flip flop. You see the pulse is given as a clock. Okay, and at the beginning it is reset. So you have, I am calling this I because it is going as input to the state machine, that conversion logic. So the I is low, but when the pulse positive edge comes, you see this is inverted and given, so that this was 0 at the beginning, then when this pulse come it becomes 1 and it remain there as long as the next pulse come. The next pulse come, it was already output was 1, so that is inverted and the 0 comes here and goes 0. So between the pulses either it is 1 or 0. Now we take it to the state machine, and state machine has some clock. It is enough if you get a pulse of that state machine clock frequency at this starting and this point, or if it is a negative edge we can make it here, it does not matter. Okay. So I will show that kind of circuit, and so this is the input which is a level, we have converted the pulse to a level signal or a pulse to a toggle signal, that is I and this is I that we are giving it here. Okay. Now this is a practical circuit. I am putting two synchronizing flip flops. We have not studied why the synchronizing flip flop is required. That is to basically to meet the setup time here. Okay. At least otherwise this flip flop can get into something called metastability. We have not studied, maybe towards the end of the lecture, end of the course I will touch upon it. I hope I will have the time to get into it, but this avoids that probabilistically. No, it is not that this scenario is completely removed, but with a high probability that is kind of that scenario is averted. That is a basic game. So do not worry about this at all. So assume that I comes here, it goes through a double stage synchronizer. It does not matter as far as timing is concerned. I1 is a delayed version of I2 is a delayed version of I1. So I2 is kind of 2 clock period delayed version of the I. Okay, that's a game. So we will see, so the pulse come like this, a toggle comes. So assume at the starting point there was a pulse here and there was a pulse here, we have converted to toggle. Now this is where the all transformation happens. We have an input, a flip flop, its input and output is combined through a logic, and assume that logic is that I2 and I3 bar. Okay. So you assume an AND gate here, I2 goes straight to the AND gate, I3 goes through a bubble or an inverter, I3 is inverted, see what happens. So assume that this is the clock to the state machine and which we use in the same this transformation circuit, and see the I2 goes like this. Okay. Here for analysis that is enough, we do not have to analyze I, and the clock comes, and when the I2 comes, you see the clock comes, so the I3 will go high. Okay. In the next clock edge, but you see that I3 we are looking for a scenario where I3 is low and I2 is high. So you see I2 is high here, but the next clock edge only the I3 will become high. So at this point with a 1 clock period there is a condition that I2 is high and I3 is low, because this clock edge only the I3 can go high because it is at the output. So I2 I3 will give a edge, a pulse which is of the duration of the clock period with a slight shift, and that can go to the state machine, and state machine is using this clock. So naturally it will sample and detect this pulse correctly. Okay. So it is a very clever circuit. I hope you got the picture. This was I2, so I2 was 0 before, and in the next clock edge here only the I3 will become 1. So before that, so during this period I2 is 1, I3 is 0, so you get a pulse, and that only happens for this 1 clock period. It does not happen here, it again happens here. Suppose you want to catch if you want a pulse at the negative edge, you do the opposite, that this point is low and that point is high, and that happens at the negative edge. You can kind of analyze it, and suppose you want the pulse at both edges, at here and here for some application, then you know that it is nothing but I2 I3 bar or I2 bar I3, which is nothing but I2 XOR I3. So depending on what you put here, maybe an AND gate with a bubble here or an AND gate with a bubble here or an XOR gate, you get any of these pulses. For our case we are going to use this. Okay. So we where we have a pulse using this particular circuit, you convert it into a level signal. Okay. And this input is goes through a double stage synchronizer to avoid some timing issue in this flip flop, and then in this flip flop we combine the input and output through a kind of this logic, very simple logic, then you get the correct pulse. And very important, the timing is correct because we are deriving with a delay with respect to this clock head. That pulse will come with a delay, and when this pulse ultimately goes to the state machine will correctly sample it as high, that is very. So this generate the proper timing as far as the state machine is concerned, because state machine is working with the same clock, that is assumption. So I hope you got this picture. It is a very useful kind of structure which is very much used in synchronizing clock domain crossing. Only difference is that I have little bit manipulated this, and when this pulse is coming from a domain with another clock, then there could be a slight change in the circuit. The pulse can go here in the data path, but the clock of the domain comes here. It is a very slight change. It is a very useful kind of principle and put together. So I am putting this at the input and side, and this as the output side, and I am combining it. So this is what which does the trick or the magic. You convert a pulse to a level signal and you synchronize it, and you convert level to pulse which is in this clock domain properly. Then the timing is proper with this clock domain. So that is how the pulses are handled. And so essentially we are saying that though we said the FSM clock frequency should be twice that of the maximum input clock frequency, we should not be worried about the pulse width, we should be worried about the frequencies. And if the pulse width, if there is a pulse, it can be stretched to be neatly detected by the state machine, okay. And we don't like in the first circuit we have shown, it is kind of stretching it integral number of the clock cycle, but then this is a better scheme. We are not even stretching it, we are toggling it, okay. It is a kind of extreme case of stretching it. We are stretching all the way to the next pulse, so it is like extremum that a pulse is stretched from the first pulse to the second pulse, then it is kind of made low, it is made to toggle, and then at the other end we convert back into a pulse which is of correct, which has a correct timing. That is the most important thing. Now let us look at this Moore and Milley output. So there is a confusion where the Moore output should be used, where the Milley output should be used. If you read a textbook, many a times it appears as if you are making a big choice at the beginning of the design, saying, because many a times it is called Moore machine and Milley machine, and that is very confusing. It is as if at the beginning of the design process you are assuming that okay let us go ahead and design a Moore machine. It is not so, because there are, in practical controllers there are a lot of inputs, a lot of outputs. Some outputs are a function of the present state, some are function of the present state and input. So it is not a question of kind of designers preference to choose Moore output and Milley output. That is what I want to bring forth. There are places where the Milley output is kind of works properly, and the best option then is to choose Milley output, okay. There are places where the Milley output cannot work, okay. At such places you should use the Moore output, and the discussion may not be complete at this point. There could be questions asked which with the present background I cannot answer you everything. Maybe as we go ahead in the lectures, maybe some issues are handled, some issues are not handled, but anyway we are improving our the grasp of the situation as we go along. So let us look at our case study where we have a controller for ADC. I will take a kind of simple case from there. There the state machine was generating a start of conversion pulse. Okay. So that is a scenario. So let us look at that state diagram. So this was the state diagram. So let us go to the slide. So if you remember, I hope it was simple enough. So at the power on we come to a state, okay, and we were waiting for the start signal from the host CPU. As long as the start was low, we remained in this state, and the SOC was, the start of conversion pulse was 0. When the start signal came, the state machine or the controller made a transition to the next state, state 1, and this particular output, I am only showing the kind of the concerned output or the relevant output. Okay. So SOC was made 1, and it's an unconditional transition. In the next clock pulse we go to S2 and make SOC 0, and we were waiting for end of conversion here. Okay. So that is a clear picture, and since this is an unconditional transition, so upon the start, like when the start is detected on the clock, it comes to S1, in the next clock it goes to S2. So you know that the pulse width of this SOC is 1 clock period, because the minimum time a state machine can remain in a state is 1 clock period, because everything happens in terms of the clock period, in terms of the clock edge. Okay. So this is a Moore output. So if you see that this SOC is a Moore output, which is a present state is decoded. That means that like when you write the output logic, we say S0 state 0. In our discussion we said it is 2 flip flops, the Q1 is 0, Q0 is 0. So we say in the output the present state is 0 0, output is 0, present state is S1 which is 0 1, the SOC is 1, present state is 1 0, SOC is 0. So it is a Moore output. During the S1 the output is 1. Okay. Now I am trying to convert this particular SOC into a Mealy output. Okay. So how we can do that? So what we do is that, say because we have only one input, the start signal, what we will do is that you look at this scenario, when the start is low, it is machine is in this state, SOC is 0. When the start is 1, transit to the next state and make SOC 1 in this state and transit to S2. So we will do like this, say we will say the machine is in S0 state, as long as the start is low remain there. Now we say instead of SOC is 0, we say SOC is 1 if the start is 1. Okay. So SOC is written as a function of start, SOC is 1 if the start is 1, then we say when the start is 1 we transit straight to the next state. So that is what I am showing here. The Mealy output is upon the reset comes here, as long as start is low remain there and SOC is equal to start. That means in this particular state, as long as start is low, SOC is low. When the start comes high, the SOC is high. That means this SOC is a Mealy output which is a function of the input start signal and the present state. Okay. So we are decoding the present state. So when you write the equation, when you write the table, we say S0 which is nothing but 0 0, and we have an input column where reach start is 0, then SOC is 0. When in 0 0 start is 1, SOC is 1. So in the equation of SOC you have Q1 bar and Q0 bar and start. Okay. That is the equation of SOC, and now we do not need S1. As the start comes in the same state, the SOC goes high and it transit to the next state and SOC is made 0. Okay. So that is the scenario, that is how the Mealy output is generated. Now we can see, and already you get a picture what can happen, and if you are clever, a clever student can already make out yes, there is an advantage saying that this particular state is kind of knocked off and you get one state less. And you can imagine if there are we are talking only about one particular output. If there are 10 outputs which was all kind of Moore kind of output, suppose we are able to translate, convert all that into milli output, maybe the 10 states are less, and that is a great saving. And 10 states are less. If it is a binary encoding log 10 to the base 2, it can be 3 flip flops could be less in the game, okay, depending on the total state. So there is an advantage. We clearly see number of states are less, but this already should give you some hint as to what can go wrong. Like we are waiting in this state and the start comes, then the SOC is 1. So that description itself should give you some picture of what can go wrong. So we are coming to the end of the lecture. So we will see that timing in the next class a little more elaborately. So because as I said we are seeing which is the optimal scenario where we can without kind of any timing issue we can use milli output and get some advantage, and where we cannot use it we should be using the Moore output is what we are discussing. So we have seen how to convert a Moore output case to a milli output case. We will look at the timing issue in the next lecture. So we have looked at basically the minimum clock frequency and the milli and Moore output in this lecture. Please revise, grasp the underlying issue. I wish you all the best and thank you.